With digital computers, we have three major ways to represent signed numbers. There's a signed magnitude, there's 1's complement, and there's 2's complement. In a separate video, we've looked at how signed magnitude works, and we identified some issues with it. Now we want to improve on that, and that's going to take us to 1's complement. So we're going to discuss 1's complement in this video. But to start, we're going to remind ourselves of the issues related to signed magnitude. So over here is a listing of all the 3-bit patterns that we could have on a machine that uses, say, a 3-bit signed magnitude representation. Now the signed magnitude part doesn't matter here. This is just all the patterns of 3 bits. A reminder, I've got the min-terms labeled here, and this is just a way to treat these bit patterns as unsigned values so that we can refer to row 3 or row 5, something like that, easily. And those row numbers will be min-terms. So we'd say min-term 5, and we would mean the row that has 1, 0, 1. So let's look at these signed magnitude values again. In the positive half of our rows, everything reflects the same thing that we would have seen in unsigned bit patterns. So this is 0, this is 1, this is 2, and this is 3. And then we had the negative values, and we made a positive value become negative, or we just perform negation in general, by taking the high order bit, called the sign bit, and flipping it. Now that left us with an unusual ordering here. We also have 2 zeros. So we've got 2 zeros, which decreases our total representational power by a single value. But also, as we do increments, while we're up here in the positive half, we move down the rows. But when we are in the negative half, if we do increments, we move up the rows. And that gives us some unusual flow, especially because as we're moving down here doing increments, when we get to positive 3 in increment, mathematically we should wrap around to the lowest value that we have. And so we jump from the middle of our rows suddenly to the bottom of the rows and then start working our way back up. So this is all peculiar, and we want to eliminate that. So we're just going to artificially eliminate it by modifying the bottom half here, because this half is solid. It looks just like what we understand in unsigned numbers. So from the signed perspective, leaving these positive 0, 1, 2, and 3 makes quite a bit of sense. But we don't like this, so let's reorder these so that they make sense. If I was up here adding 1, then I would be moving down the rows. If I was up here subtracting 1, I would go up by rows, up 1 row at a time. So I want that same thing to be reflected down here. So when I'm going down the rows, because I'm adding 1, I'll go from 0 to 1 to 2 to 3. And if I add 1, again, I really should go to, I should wrap around to the lowest number we can represent, which will be negative 3. But I want that flow to continue to here. So I'm going to put negative 3 here. I'll leave these other numbers alone. So we'll have positive 0, positive 1, positive 2, positive 3, and then come to negative 3. So we're totally wrapping on the values here, but we haven't wrapped around the rows. Now, negative 3 plus 1, I want plus 1 to go down again, so that would be negative 2 here. And then negative 1, and then negative 0. Right? So we still have the same 4 values in the bottom half. The only difference is that we have reorganized them just arbitrarily so that increments go down and decrements go up, regardless of which half you're in. So down here, for example, if I subtract 1 from negative 1, I'll go to negative 2. Decrement again, that's negative 3. Decrement again, it would be negative 4, but that's outside of our range. So like an odometer, we're going to wrap around in the values. And that will take us to the highest value, positive 3. Subtract 1 again, positive 2, positive 1, and so on. The only place that this gets weird is when we are up here at positive 0 and we subtract 1. If we were to wrap around our rows and come to here, we would have ended up at negative 0, which is really the same value. So that doesn't work. We'll still have to come up with some mechanics behind the scene if we're going to implement this thing to where wrapping around from positive 0 or negative 0 doesn't take you to the other 0, but takes you to the appropriate signed version of a magnitude 1. But when we do this reordering, we've effectively introduced what we call 1's complement. So really, this row is 1's complement, or this column is 1's complement. This column that we had in the past is sign magnitude. Now, not only do increments go down and decrements go up, but we also have an interesting relationship now between the bit patterns of individual values. So let's take positive 2 as an example here. When we have the bit pattern for positive 2 with this representation is 0, 1, 0. And that's the same regardless of our signed representations when we're in positive numbers. So 0, 1, 0 is positive 2. If we look at negative 2 now, it's the bit pattern 1, 0, 1. Let me put those a little closer for you. So positive 2 is the bit pattern 0, 1, 0. And negative 2 is the bit pattern 1, 0, 1. Now we'll go back to the table and pick some others. Let's try 0. So positive 0, back here in this table, you'll notice is 0, 0, 0. But negative 0 is 1, 1, 1. So we have 0, 0, 0, and 1, 1, 1. If we were to look at something else, let's just say positive 3 and negative 3. Positive 3 is 0, 1, 1. And negative 3, where's negative 3? Here's negative 3, 1, 0, 0. So what do we see? Well, it turns out that in this 1's complement representation, where we've effectively only reordered the bottom half of the rows of our 3-bit table, we see that the negative bit pattern of a positive value is always the same thing as it was in positive, except for that each bit has been flipped. So in sign magnitude, we negated a number. We went from positive to negative, or negative to positive, but just isolating the sign bit and flipping it, and leaving all other bits alone so that they could just represent the unsigned magnitude. But in a 1's complement representation, to negate a value, we flip all the bits. Now this is referred to as 1's complement negation. So 1's complement negation is really the same thing as flipping all bits or inverting the value. And that can be done really nicely digitally with an inversion circuit. But this is also referred to as 1's complement negation. So flipping all bits, 1's complement negation, or inverting a bit pattern, all of those are effectively the same thing. So 1's complement numbers are those who are represented such that inverting all the bits gets you the negative of the original. So we go from x to negative x by inverting all the bits. Now let's look at some bit patterns then and try to evaluate them. In other videos we did this with a 5-bit machine, so we're going to do the same thing here. Let's look at a 5-bit 1's complement system. So again, the highest order bit will be the sign bit. We just need some values to work with. Let's try 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, and 0, 1, 1, 0, 1. Now, recall, we can immediately identify the sign of the values these represent based on that high order bit, the sign bit. So we predetermine that each of these that starts with a 1 is going to be a negative number. So negative here, negative here, negative here. All the ones that have a 0 there, or start with a 0 in that high order bit, those are going to be positive numbers, just as we saw before. Now, one real benefit here, again, is that with the positive numbers, the 0 that's leading the front, the 0 in the higher order bit position, effectively doesn't change these values from their unsigned representation. So if we know that it's positive, it's going to be the same value we would read if we were to look at this as just an unsigned number. Right? So let's take care of those. In this case, we're looking at these bits effectively now just being magnitude. So this is 8 plus 2 is 10. Here we are with another one that's positive. This is 8 plus 4, 12, plus 1 is 13. So very quickly we identify that those are positive 10 and positive 13. However, for these other ones, it's not quite so obvious what this bit pattern represents, because at face value there's a 1 in the 4's bit and a 1 in the 1's bit, which seems like a 5. But this is not negative 5. If this were negative 5, this would have to be a sign magnitude representation, and it's not. It's a 1's complement representation. So the only way to interpret this is to actually negate this particular bit pattern. So what we're really looking for is the negative of whatever the flipped bits here are. So I'm going to say this is negative, and then I'm going to write a bit pattern as an unsigned value. That's me just flipping all these bits. So 1, 0, 1, 0. All I did was take these 4 bits and flip them. Now I can reinterpret this as an unsigned value to be the magnitude associated with this sign. So this is the 8-bit and the 2-bit, which is 10. That means this whole thing is negative 10. Right? The original bit pattern, 1, 0, 1, 0, 1, is negative 10 decimal. Now we'll do the same thing here. First I'll flip all the bits so I know what binary I'm dealing with. So that's 0, 0, 1, 1. So the negative of whatever 0, 0, 1, 1 is going to give me my final value. So that's 3. So the answer here is negative 3. For this one, flip all the bits again. So and I'm just really concentrating here to get the interpretation. That's a 1, 0, 0, 0, that's those 4 bits. And that is an 8. So that means the whole thing is negative 8. Now, I want to point out that when I flipped these bits, I was only looking at the bottom 4 bits. Right? I knew that this was the sign, and I knew that these bits also had to be flipped for me to see the bit pattern to interpret. But the interesting thing is, instead of having to have that extra bit of knowledge in the mechanics for this, where I separate the sign bit from the rest of it, in 1's complement, unlike sign magnitude, I just treat all bits the same. So in reality, I can flip all the bits to find out what the positive version of this value, of a negative value, is. So I know because of the 1 to print out a hyphen or a minus symbol to indicate that this thing is a negative value. But then to find out its magnitude, I could take it from this more obscure bit pattern, which is negative and not so obvious to me, and then negate it and make it positive, in which case it's the absolute value. But that means flipping all the bits. The nice thing here is, if it was negative and I did this in the first place, that sign bit for all of these, at least the 3 that I have to do that with, they're all 1, so when I flip them, that's the same thing as adding an additional 0 to the front, which doesn't even change the way I interpret these, right? So this still looks like 10, this still looks like 3, and this still looks like 8. That's because it is. We just sort of mentally noted that each of these were negative because in the original value there was a 1 in the sign bit. Right? So this is not that bad at all. Now let's do the same thing for trying to go from some decimal value that's within the representational range of this system down to its bit pattern. So again, we are going to stick with a 5-bit 1's complement machine, or 1's complement representation. All right, and let's convert the numbers 6, negative 11, negative 13, 3, and negative 4. All right. So For the positive values, 6 and 3, this is really easy for us. Since we didn't reorder the original table that we had started with, right? Since we didn't reorder this top half, we left it alone. All the values are the same in sign magnitude, all the values are the same in one's complement, they're the same in unsigned. Because we didn't mess with those, any value that is a positive decimal value, like positive 6 and positive 3, that we want to convert into its binary equivalent in one's complement, we just write down the unsigned number, restricting it to 5 bits. So a 5-bit version of 6 is 0, 0, 1, 1, 0. This is the 4-bit and the 2-bit, 4 plus 2 being 6. And then for positive 3, we have no 16s, no 8s, no 4s, but we do have a 2, and we do have a 1. And that's all it takes to get those values converted. It's a little more difficult, however, initially, to figure out how we can just plain write the bit pattern for negative 11. Unlike sign magnitude, we can't just write down the bit pattern for 11 and then put a 1 in front of it to make it negative. Because for one's complement representations, negation involves flipping all the bits. So the safest thing we can do is understand that negative 11 is really the equivalent of the negation of positive 11. And negative 13 is really the negation of positive 13. And negative 4 is really the negation of positive 4. All right, so then we can start to do a little bit more. So how do I represent positive 11 in 5 bits one's complement? Well, that's not so hard. I'm just going to put a negative sign in front to remind me that I need to negate this thing in the end. So now I'm going to write the 5-bit pattern for 11 and then later just negate it. So the 5-bit pattern for 11 is not any 16s. We'll definitely need 8. No 4s, because that would make 12, and that's too big. 8 plus 2 will give us 10, plus 1 more gives us 11. So there's the 5-bit pattern for 11, positive 11, and later we'll negate it. Negative 13, well, that'll be no 16s. We'll need 8 plus 4 to get 12, and 1 more to get 13. Negative 4 is really the negation of positive 4, and 5-bit positive 4 is 0, 0, 1, 0, 0. So now we're almost done. We have a 5-bit representation of the absolute value of these things, and now we just need to negate it. But negating in one's complement is flipping all the bits. So in the end, that gives us, flip all the bits, 1, 0, 1, 0, 0, 1, 0, 0, 1, 0, and 1, 1, 0, 1, 1. So I'll underline, just to make it extra clear, each of the final bit patterns that represent the original signed decimal values that we were trying to represent. Now, of course, we might want to ensure that we did our work correctly. So I'm going to take 2 of these bit patterns. I'm going to do negative 13 and negative 4, and we'll evaluate those. So this is negative 13 here. That was the bit pattern 1, 0, 0, 1, 0. Right, we assume that this is negative 13. Then we had the bit pattern for negative 4, which we think is 1, 1, 0, 1, 1. Right, so negative 4, we think, is 1, 1, 0, 1, 1. Now, if we're right, then the basic rules of one's complement should allow us to automatically decode these as negative 13 and negative 4. Further, we ought to be able to negate them and get positive 13 and positive 4. So we're going to do both of those things. Let's start with just evaluating the bit pattern as is. So we see there's a 1 here, so we know that this thing is going to be negative. Right? Now we're going to flip all the bits to figure out what that is. So that'll be 0, 1, 1, 0, 1. Right? And then we have to reinterpret what these bit patterns mean. So this is 8 and 4 is 12, plus 1 is 13. So negative 13. Great. Negative 4. Here's a 1, so we know this is negative. We'll write the negative symbol. And then we'll do 1's complement negation here, flipping all the bits to get 0, 0, 1, 0, 0. And now this appears to be negative 4. So that worked out just fine. Now the second way I said is that we could double check this is to verify that if we apply negation, 1's complement negation, where we just flip all of the bits, if we started with the bit pattern for negative 13, we ought to get the bit pattern for positive 13. And if we start with the bit pattern for negative 4 and we negate it, we should get the bit pattern for 4, positive. Now we can actually see that we've already done that, because here we flipped each of those bit patterns. We just put the little negative symbol in front so that we abstractly understood that it was originally a negative number. And then here's what that absolute value was, those positive values. There's 13, there's 4, just with the little marking in front to remind us that it was negative. So in fact, that our answer has worked out just fine. So lastly, we need to deal or just mention a few things here. So what we've done in going to this 1's complement notation from the sign magnitude notation is very minimal. We just reordered the bottom half of that table. We didn't actually change the range that we can represent. So with 1's complement numbers, since we just reordered the numbers that were already there in sign magnitude, we have the same range. So given n bits, we can go from negative to the n minus 1 plus 1, all the way up to positive 2 to the n minus 1 minus 1. So the same range as sign magnitude. We also, like sign magnitude, have two zeros, positive 0 and negative 0, which is weird. But we did get the positive effect of having increments and decrements move in a consistent direction through our min-term rows, which is great. The only thing really that we want to deal with is that we've got two zeros, which causes more than one problem. The two zeros is weird because there's two of them. It's also weird because it takes away one of our representable values. With a 3-bit system, we can have 8 different values, but we really only end up with 7 different, we can have 8 different bit patterns, but we only have 7 different numbers because we have 2 zeros. When we have 5 bits, we could have 32 values, but we only got 31 because we had 2 zeros. So we want to take care of that. Additionally, we don't want the 2 zeros because when we get, even in our current reordering with 1's complement, when we get to the top of the rows and then we subtract 1 again from positive 0, if we were to wrap around the rows physically and end up on the bottom side, then we're back at 0 again. And we need to eliminate that to improve the overall value of our representation. And that's what we're going to do with the 2's complement representation.